Hello, welcome to the online course on interpretable and explainable artificial intelligence, also known as XAI. XAI is a new and emerging subfield of machine learning, and this course will give you an overview of XAI by discussing works that have been developed in the last 5 to 10 years. The broad goals of this course are to understand what is meant by interpretability and explainability in machine learning, to outline when and why they are important, and to learn some of the state-of-the-art methods and approaches in this field. In this first lecture, we will start with a broad introduction by covering a couple of important examples. Then in the following lectures, we will go into the details of different approaches. We live in an age where machine learning algorithms are introduced at all levels of the society. Data-driven algorithms are progressively used in many different fields, including medicine, justice, self-driving cars, banking and loan applications, hiring decisions, and scientific discovery. On one hand, there are great hopes that data-driven algorithms can help us with important decision-making. At the same time, there is a growing concern that algorithms are deciding our fate while we don't understand what they're really doing. So there is a fundamental tension here. Artificial intelligence can help, but there's an increasing lack of trust. This is precisely what explainable artificial intelligence is aiming to address. Let's start going into the details. How does machine learning build decision-making algorithms? This figure illustrates the general machine learning pipeline. Machine learning uses available data to learn predictive models. Typically, the data consists of a set of input-output pairs, such as a set of images with corresponding output labels. Machine learning algorithms then train mathematical models which transform such inputs into outputs. The models are trained by changing parameters to optimize accuracy defined by a cost function. The ultimate goal is to obtain a model that will predict accurate outputs for new inputs not included in the training dataset. This is potentially a very powerful approach, but it has several important issues. A central goal of machine learning is to build models that learn causal relations from data. But the key issue is that in practice, machine learning algorithms have access only to correlations in the training data. A fundamental problem is that correlations do not always reflect causal relations. Let's look at a toy example to illustrate the fundamental difference between correlation and causation. Imagine you plot on the same graph the number of ice cream sales and the number of sunburns as function of the month in the year. The two vary together, they're highly correlated in this toy example. Based on this correlation, a trained model would learn that high ice cream sales predict a high risk of sunburns. Does that mean that buying an ice cream causes a sunburn? Well, obviously not. What is happening here is that there's a hidden factor, sunny weather, which leads to both sunburns and ice cream consumption, and therefore generates a correlation without causation between the two variables. For that reason, when two variables are correlated, either there is a real causal link between the two, or the correlation is generated by a common variable, usually called a confounding variable. This is often called a spurious correlation. So one key issue with machine learning algorithms is that they might learn spurious correlations rather than real causal relations. A second issue with the general machine learning approach is that the models that are trained to make predictions are often what we call black box models. Black box models are going to be one of the key concepts of this course. So what is a black box model? Fundamentally, a black box model is a model that does not reveal its internal mechanisms. Why doesn't it reveal its internal mechanisms? There are at least two possibilities. One possibility is that the model is too complex and simply cannot be directly understood by looking at the parameters. A second possibility is that it is a proprietary model, so that we don't actually have access to the internal mechanisms of the model. Why are black box models problematic when used to make important decisions? A long list of issues have been identified. These issues include the reliability and robustness of black box models, their safety and therefore how much we can trust them. More generally, a key issue is how fair are these models, and conversely, whether they are intrinsically biased. Fundamentally, all these issues are related to the question of whether a model learns causal relations or spurious correlations. And with a black box model, this is difficult to tell. Let me now illustrate these issues with a couple of concrete examples. Here's the first example: computer-aided medical diagnosis. In this example, the goal is to use an artificial intelligence model to detect pneumonia from chest radiographs. A very influential paper written by Rajpukar and colleagues developed an algorithm called ChecksNet that makes this prediction with very high accuracy. This model is a neural network, a model too complicated to be understood and therefore a black box. This model, as many other models, was trained and tested on different subsets of the same dataset, as is standard in machine learning pipelines. But a key question is how well does it generalize to a completely new external dataset? Concretely, if the model was trained on data from one hospital, how well does it do when tested on data from another hospital? A follow-up study has examined this question and found that the performance is strongly reduced when the model is used on data from another hospital. This presents clear reliability risks if such a model is deployed in the health system. Why was the performance reduced when testing on data from a different hospital? The central problem is that the distributions of data are very different across hospitals. In particular, there are large differences in the prevalence of pneumonia. A follow-up study by Zach and collaborators analyzed the trained network and showed that instead of identifying pneumonia, the network learned to accurately identify the hospital in which the X-ray was taken, and more specifically, the machine that took the X-ray. In particular, it turned out that in one of the hospitals, the radiology technician always placed a metal token next to the patient, which can be seen in the top right corner of the radiograph. And the network model in fact learned to detect that token. So this is a concrete example where a black box model learned spurious correlations rather than a causal relationship between the image and pneumonia. Let's now turn to a second example: emergency room management in a hospital. In this second example, the goal was to use a machine learning model to predict the probability of death of patients coming in the emergency room with pneumonia. The goal was to use this algorithm to help decide whether the patient is high risk or low risk, so that a high-risk patient is admitted to intensive care right away, while a low-risk patient is treated from home to save space in intensive care. To make this decision, the model used patient data such as age, gender, and medical history, whether the patient has, for example, chronic lung disease, asthma, and so on. A set of models were trained on data available from previous patients in the hospital, and the most accurate model turned out to be a neural network, a model too complicated to be understood, and therefore a black box. Very surprisingly, when inspecting this model, researchers found that it predicts that patients with asthma are low risk. This is simply wrong. For a person with asthma, pneumonia is in fact fatally dangerous. This illustrates the fundamental issue with trust in black box models. Why did this model learn to make this prediction? The model was trained on data from previous patients in the hospital, and it learned a pattern that is present in the data. Previous patients with asthma were usually admitted directly to intensive care, which reduced their risk of death. The problem here is that the data was biased. In this case, it would not have been ethical to collect data without this bias. And the model learned this bias rather than the real causal link between asthma, pneumonia, and risk of death. So ideally, a specialist, a medical doctor, would need to check the overall pattern of predictions learned by the model. But because the model is a black box, understanding the pattern of predictions is simply not possible. The third and final example is the use of algorithms in criminal justice. In some countries, algorithms are used to predict the risk of future crime of an inmate based on available data, in particular their criminal history. Concretely, companies develop algorithms that are trained on inputs such as prior arrest, alcohol and drug abuse, and so on. And they predict outputs such as the risk of arrest, risk of drug use, or risk of violence. These predictions then help make decisions on bail, on whether a person goes to jail and for how long, and whether they are released on parole. These algorithms are black box algorithms, not necessarily because they're very complicated, but because they're proprietary, sold for profit, and not open source. So we don't know how these algorithms work. This raises important issues which have attracted a lot of attention, in particular in the mainstream press. An article in the New York Times described a specific case in which an inmate was denied parole because of the prediction of a proprietary black box algorithm. The problem is that after an investigation, it turned out that the algorithm made the prediction because of a typographical error in the inputs. So a typographical error kept the person in prison, obviously a dramatic mistake. This specific case illustrates the importance of explaining to a stakeholder, such as an inmate or a lawyer, how an algorithm reached a decision. Moreover, the stakeholders need to have the possibility to challenge the decisions of the algorithm. This is an illustration of the fundamental problem of fairness when black box algorithms are used to make decisions. Another article, a long investigation reported by ProPublica, examined the effect of race in decisions reached by algorithms used in criminal justice. In this article, the authors argued that the algorithms might be fundamentally racially biased, meaning that they predict a higher risk of crime based solely on a difference in skin color. This is another fundamental issue with black box algorithms. They're likely to reproduce biases present in their training set, again because they learn correlations rather than causal links. The three examples I went through illustrate some of the fundamental issues with using black box algorithms: the lack of reliability, robustness, a lack of safety, trust, fairness, and fundamental biases. The central underlying problem is that the classical machine learning pipelines do not take these criteria into account when training models. In fact, we simply do not know how to include these criteria directly in the cost functions that we are optimizing. So instead of directly addressing these criteria, the remedy that has been proposed is to develop methods to interpret and explain black box models. The idea is that having models which produce decisions which can be interpreted or explained to human users is a way of ensuring reliability, safety, trust, fairness, and fundamentally a way to produce knowledge from data. But what does it mean to interpret a decision of a machine learning model? Fundamentally, to interpret means to explain or present in terms understandable to a human how an algorithm reached its decision. Importantly, this does not imply understanding the details of the algorithm. Instead, this means giving arguments for how inputs led to the output, so that these arguments can be examined, trusted or not, or challenged and appealed if needed. How does this work? What kind of explanations can algorithms give for the decisions? Let's again go through a couple of examples. First example, let's imagine an algorithm takes as an input a set of medical symptoms and other variables, such as sneezing, weight, and so on. And then the algorithm outputs a decision, a diagnosis, for example, flu. The algorithm can give arguments for how it reached this decision by giving a set of scores that indicate the importance of each of the inputs for the decision. In general, such scores are called feature importance scores. This will be one of the important concepts in this course. In this example, the algorithm would output high scores for sneezing and headache as evidence of flu. Then a human specialist, a doctor, can inspect those scores and validate or not the decision, depending on whether it makes sense or not. Second example. Let's imagine a person applies for credit and an algorithm denies the credit based on the input it's received. The applicant would then want to know why the credit was denied, and more specifically, what they could change in the application to change the outcome and get the credit. For example, the algorithm could say, "I'm sorry, your credit was denied, but if you change the requested amount, the duration or the purpose, it would have been accepted." More generally, the algorithm could give a set of actionable options that would change its decision. Such actionable options are a type of explanations that are called counterfactuals. A third and final example is an algorithm that gives the full causal chain, which explains how inputs are transformed into outputs. Let's consider the case of criminal justice, where the goal is to predict the risk of future crime. Let's imagine that we have an algorithm that gives points to different aspects of the criminal history of a subject, then sums these points, and then predicts the arrest for any offense if the sum is larger than 1. Here we have an algorithm that is totally transparent. It is the opposite of a black box, and it provides the full comprehensive explanation for how it reached a decision, so that the judge can validate it or not, and the subject can appeal it if needed. This was the final example, and this brings me to the end of this first lecture, which was a broad introduction to explainable machine learning. We went through the fundamental issues that explainable machine learning aims to address, and illustrated a couple of approaches for generating explanations. In the next lecture, we will dive into the details and talk about different types of explainable machine learning. See you next time!